Hi there, so today we are talking of Moshi, the last AI from Qt, which is a speech text model, and it has been released just few weeks before the advanced voice mode of ChatGPT, which is also a speech text model. But they didn't release any technical report, but we have the one of Moshi. So we will go through this report of 67 pages, and the goal of this video is to have a high overview of their work. So let's begin. So here is the bubble of Moshi and its four main components that we are gonna see during this video. But first of all, I would like to read with you the abstract. On the very first sentence, I've highlighted the term speech text foundation model. So I would like to define this by showing you what is not a speech text foundation model. So, in traditional speech-to-speech pipeline, you have often a speech-to-text model. Then you have your LLM, Llama, Falcon, GPT, I don't know. And then you have your neural synthesizer to reproduce the voice from the text. So this shows several limitations. First of all, it has a huge latency because every block is handled by huge neural networks. And then right there, you have an information bottleneck because you are representing the conversation only with text. And so you cannot convey the emotions with this modality, for instance. So it's not the best. Then, in the abstract, they are talking about a full duplex spoken dialogue system. Here again, I'm showing you what is not a full duplex system. It's the walkie-talkie. A full duplex system is a system where two users can speak and listen at the same time with overlapping speech, as you see. Okay, so now let's get a bit more technical. They are talking about a residual quantizer of audio codec, and then they are talking also about hierarchical semantic to acoustic token. So I would like to do a quick reminder about what are semantic and acoustic tokens. This recap belongs to the MIMI part. So first of all, we will see what are semantic tokens. For instance, you can extract semantic tokens with networks such as Hubert and WaveLM. Here I took the figure from Hubert. So basically, semantic tokens are a high-level representation of audio. And to build these tokens, usually you are passing the raw waveform to a transformer network, and then you are gonna mask some of the embeddings at the output of the conventional encoder, and the transformer network will try to retrieve those mask tokens. In fact, the task, to be more precise, is to retrieve the cluster of the mask tokens. So at the beginning, they instantiate the clusters with the K-means algorithm on the MFCC, and then they refine the clusters using the networks. But the message is that once it is trained, the semantic tokens represents like the semantic information, and I would like to show you a graph which I find very interesting. So this is a dendrogram of the final discrete speech units of Hubert, and you see that when you have embeddings that are close, they often refer to the same type of sound. So for instance here vowel, and then here you have fricatives. So it is easy, if I can say, to create an audio that makes sense with this kind of presentation. On the other hand, you have acoustic tokens. So at the beginning, the acoustic tokens were introduced to compress audio information to beat the MP3 format, for instance. and they are working more on the waveform domain. So this figure is taken from the Encodec article. The goal of the architecture here is to approximate the identity function. So you should have the same waveform here and here, but you have a bottleneck there. So the networks need to represent the acoustic information that is more relevant to reconstruct the waveform here on several codebooks, because here you have a continuous embedding that will be quantized on the first codebook, and then the residual will be quantized again on another codebook, and so on and so forth. So with this representation, you end up with something like that. So here you have the temporal axis, and there you have the scale of the codebook. So you have several indices at the same timestamp. And you see that this network is trained with a lot of losses, and those losses are reconstructive losses in the temporal domain, so L1 norm on the waveform, or on the, you can also have some losses on the spectrograms here. And most importantly, you also have an adversarial training thanks to discriminator, and you have adversarial losses, so the usual one. The generator is trained to confuse the discriminator, and to do that, it needs to output something that seems like it was not compressed. And you also have a feature matching loss. So it's a lot of losses to just to make sure that the audio at the end is of high quality. And by doing that, you're gonna construct acoustic tokens like that on several scales. And then Mimi, which is an hybrid tokenizer that can extract at the same time semantic and acoustic tokens. Here is the architecture, and I'm gonna highlight some interesting points on it. First of all, you have the WaveLM network that can extract very good semantic tokens, and they have performed distillation on the very first scale of the codebook here to retrieve the semantic information extracted by the WaveLM network. Then they have also used adversarial losses, which are a feature matching loss on the embeddings of the discriminator, and an adversarial loss, which is the classical one, just as we've seen on the encodec training. But you don't see any reconstructive loss in the waveform domain, because they find out that it was good for the metric, but not good for the quality, to have L1 norm in the temporal domain or STFT loss. From my personal experience, you can still have a multi-scale STFT loss, but you need to apply a perceptual weighting, so it will not degrade the quality. But the most important losses are the adversarial ones if you want to have a high quality signal. So those two losses here, the distillation loss and the adversarial losses, it's what makes Mimi an hybrid tokenizer, semantic and acoustic. Then they are also the first to use a transformer in the decoder and in the encoder of the codec. So transformer is a powerful architecture, and in the paper they found that it was improving the results. So they added one. Another interesting point here is that they are using a split RVQ. You see here they could have performed the residual quantization on the first scale here, but as it represents the semantic information, all the subsequent codes would have also tackled this. But this is good for phonetic discriminability, but not so much for audio quality. So it's better here to have two separate quantizers, so one quantizer at a single scale for the semantic information, and the residual quantizer here for the acoustic information. So on this part, the network can focus on all the details that are missing to reconstruct a high quality waveform. And here you only care about trying to approximate the waveLM embeddings. Okay, so now a little ablation study about Mimi. So I'm gonna focus here mainly on the ABX metrics, which measure the phonetic discriminability. And here, the Mushra, it's human people that ranked the sound from 0 to 100. Higher is better. So you see at the first line, it can be considered as a vanilla at the vanilla codec, and you have quite good Mushra, but the phonetic discriminability is not good at all. And when they introduce the distillation of waveLM, the metrics is much better, but you lose on the quality. And when you have at the same time here on the last on the fifth line, the distillation and the split quantizer with the transformer both at the decoder and encoder, you have a good Mushra and a good phonetic discriminability. Also, we can notice that the transformer in the decoder is more important than in the encoder here, if you look at the Mushra, because I think it can be interpreted as the fact that you can't have a one-to-one mapping between tokens and sound, and you need to study the tokens in their context. So you need to have a good modelization of the sequence of tokens when you are decoding the signal to produce a relevant waveform. To finish on Mimi, they perform a comparison with state-of-the-art codecs. I'm just gonna look at this codec, speech tokenizer. It's a codec that also perform semantic distillation, so it has a good phonetic discriminability. But Mimi has a much better Mushra and still a good phonetic discriminability, so it has the best of the two worlds of semantic and acoustic tokens. And by the way, you notice that when you add temporal losses, the quality perceived by human is not as good, even though the metrics are better. But the end goal is that listeners like the quality of the audio, so they selected this version of Mimi. And also you see that on the bitrate column, Mimi has the lowest one, meaning that it can compress information very highly. And to compute this bitrate is very simple. You just need to think about the number of bytes per second. So for Mimi, I've done the math for you. It's here the sampling rate of Mimi. You have 8 scales, and here I'm gonna explain it the log2 cardinality of the codes because you don't need to transfer the entire embedding. You just need to transfer the index in the codes of the index of the codes if the transmitter and the receiver knows the codes. So at the end, you have 1.5 kilobits per second, kilobytes. Just one thing that is missing, I think I would have liked to see a comparison with the recently published big codec. I think it appears just before Mimi, which is a codec that is only focused on the acoustic tokens. And I think this big codec tokenizer have also a very high Mushra. I would have been interested to see this comparison. But still, Mimi has a very good mushra too, almost the same as the ground truth. Now that we've seen how the blocks are made, we are gonna see how to build on top of them. So we are gonna tackle the Helium LLM. I'm not gonna go through many details here because it's not my research field, but I would say that Helium is a very good LLM utilizing all the modern training techniques. They are using rope positional encoding, which is an hybridation between absolute and relative positional encoding. I think it's a good idea for audio. Flash attention to perform the attention formula faster on the hardware. Good activation function. They use sentence piece tokenizer, which is very handy. They train with Adam weights decay, which is quite important when you are dealing with large neural networks with a lot of parameters. And also they are using a good scheduler, cosine 1, to decay the learning rate. And now about the hyperparameters that are used in Helium, in the model and in the training. We have this table, and you see here that they are talking about the Helium training, pre-training, and then they are talking about Moshi. Little spoiler, Helium will be incorporated in Moshi, but before they have pre-training it only on text, and then they have done an hybrid training with text and audio, and finally they have fine-tuned it only on audio. So I would like to talk about the different phases here of training, and notably about the data that they've used. So here the goal is to build a large language model with good capacity, and to see a lot of text. So they have used Wikipedia, Stack Exchange, and Common Crawl with data filtering. And then that the model is able to generate text with a good perplexity, they have performed here a pre-training, and the model was using text and audio, and it was also a big training with 7 million hours of audio, and for the text label they have used Whisper to transcribe the audio. Then in the post-training, it is here where the Moshi model learn is a multi-stream ability. So they need some data set with several channels where you have speaker 1 and speaker 2 to play either Moshi or the other user. So they use Pianot to diarize the dataset. Then there is a feature which is this time a real dataset of conversation. And finally, they have fine-tuned it with an in-house dataset of a voice artist. So I want to highlight several things on this table. So first of all, they have using here, I'm more familiar with audio, but I think 1.2 million token is also huge, but 16 hours of audio is huge. So they really performed a large training, I think, with a lot of GPUs. And then it's what I was saying before. You have the pre-training of Helium with only text, and then you have the fine-tuning with audio only. And we are gonna see also that we need to put some delay on acoustic tokens so that the model can be more performing by knowing what semantic and text token it has predicted to perform the prediction of the acoustic tokens. And then the audio cardinality is only 2048 because you don't output all the scales of the acoustic tokens at the same time, but you rather have a transformer network that will do this prediction autoregressively, which is the RQ transformer that we are going to see. But before tackling the RQ transformer, I would like to show you the different patterns we can have when modelizing the acoustic tokens. So this is a raw pattern that you have at the output of the encodec network. So for your different timestamps, you have the indices of the codes. And this figure is coming from the music gen paper, which is generating music with the encodec tokens. So this is the first pattern they propose to use. You feed the sum of the embeddings of given timestamps to the transformer network, and it will output the indices of the next time steps, but you will have several heads to the transformer model to predict every code. So this is not giving very good results because you're not utilizing the prediction of the scale number n to predict the indices of the scale number n plus 1. So they rather propose to flatten the pattern here. So you will have more time steps, but you can utilize your prediction of the code number 0 to predict the code number 1 at the same time steps. So this is giving better results, but you see that you're increasing the length of the sequence a lot by multiplying it by the number of codebook scales. So it's not very good for the complexity of the transformer, which I remind is the length square of the sequence. So you can have an alternative, which is the coarse first. So you just predict the first scale, and then you predict all the other scales at the same time with the transformer. But it's not the best because you still multiply by 2 the length of the sequence, and they find that this delay pattern was the best. So you just introduce a small delay that is negligible at the sequence length, and you can use your prediction of the last time steps to predict a scale more. Another work that is coming from the NLP literature that I want to talk about for you to understand the final architecture of the RQ transformer is the megabyte paper. So when you are dealing with very long sequences, instead of having just a single model that will have a high complexity to model all the sequence, you rather have two models, a global model and a local model. So the global model will modelize the grouped tokens here, and then you can decode at the token level with the output of the embedding of the global model thanks to a local model. So given the works on MusicGen and the work on Megabyte, they propose the RQ transformer architecture. So this RQ transformer is composed in fact of two transformers. There is a temporal transformer here and a depth transformer. So they grouped all the tokens at the same time step. So here step S-1 for code book number 1, 2, 3, 4. and they feed it to the temporal transformer that will output a temporal complex vector, and this vector will give the context for the depth transformer to give the predictions of the codes at the next time steps given the input of the system. So I said before that this temporal transformer was in fact Helium that they have fine-tuned here to predict the temporal context. But before, they were predicting text. So this temporal context is given by the temporal transformer. And here we have the logits of the step S and the codebook Chi given by the depth transformer. So n chi here, k, is the cardinality of the codebook k. And one thing that they have omitted in this figure is that they still output the text here with a single linear layer on the temporal context. And finally, to train the network, they compute the cross entropy here on the text, and they also compute the cross entropy on the different codes. So you have a parameter here to adapt the importance of several codes. So they put higher importance on the first scale of the code book because it's the semantic layer, and it's more important. And this text prediction here helps the networks to produce more structured outputs, not only at the acoustic level, but at a longer context, like 1 minute. The speech that Moshi produces makes sense because it is guided from text. They said in the technical report that it is an extension from the coarse to fine scales. It's a text to coarse to fine predictions. And now an ablation study on the RQ transformer. So you have here the RQ transformer. It's activated, or when it's not activated, it's a single temporal transformer with 8 different linear heads to predict simultaneously the different codes of the different scales. So if you have this acoustic delay, you see that the perplexity is quite good in the two cases, because here you can still use the prediction of the codebook scale number 1 to predict the codebook number scale number 2, because you have an acoustic delay. But if you use this acoustic delay, the transformer will have a single embedding on which you will have all the linear heads that will be plugged to predict all the codes, and it cannot rely on the prediction of another scale. So it's not good at all. You see that the perplexity is very high. And rather than in this case, the RQ transformer outperform all the other setups because it is doing the prediction autoregressively of the scales from coarse to fine. And finally, inner monologue, and more broadly, how Moshi is modeling the input and output streams. So they have done this figure in the article. At the top of the dash line here, it's tokens that are used as inputs, and here it's the output of Moshi, the tokens that are sampled from the RQ transformer. So I would like to highlight several points. First of all, what they are calling inner monologue, in fact, is that Moshi is still predicting text when he speaks, which is guiding the sequence to be coherent on a long temporal context. And then you see that there are no specific time where Moshi needs to speak and the other is speaking. You see that you have overlapping segment here. So Moshi, in fact, is listening and speaking always at the same time. But you see that Moshi here is not talking because the predicted text token are pad token, which are modeling silence, but it is always outputting some acoustic tokens which are close to silence. And when the model starts to talk, it outputs the EPAD token. So you can also control Moshi, and for instance, you can hard code the EPAD token at given timestamps, and then it will start to talk on the next timestamps. And Moshi is so of course I will do a little demo at the end with the web UI, but if you deep dive in the model, it can be used for a lot of use cases, and it has a lot of adaptability. So yeah, I was talking about the acoustic delay on the RQ transformer here. The delay was 0.222, but in the fine-tuning steps, they just add a delay of one token to have a shorter latency because 2.5 Hertz is 80 milliseconds. So you need 80 milliseconds to predict this and to predict this. So it's an overall algorithmic latency of 160 milliseconds, and we add on top of that 40 milliseconds of computational latency, which is overall 200 milliseconds, and that's why Moshi is so fast. And I want to talk more about this acoustic delay. I will not go through all the details, but Moshi is also a zero-shot automatic speech recognition system as well as a text-to-speech synthesizer. And by playing on this acoustic delay, you can have this kind of behavior. So, for instance, if you put the acoustic delay on the other way around, meaning that to delay the text prediction from the acoustic token, you will have a speech recognition system. And also it's possible to create with some specific delay a text-to-speech system. And also, the first time I used Moshi, I was wondering how Moshi is not bothered by his own prediction when he speaks. How does he recognize only the voice of the user? So it's because they have performed implicit acoustic feedback constellation by adding the input tokens in the user streams with a small factor and a randomized delay in the fine-tuning stages. So the Moshi model is robust to what it is outputting, and it will do source separation and only focus on the user stream. Yeah, and the last remarks, this could have been done at the codec level into Mimi, but they rather have done it in the fine-tuning stage on the RQ transformer because Mimi is frozen in all the steps of the training of the RQ transformer. And we end this presentation by bursting the Moshi's bubble with this figure. So you see that Moshi here is a speech text foundation model which will handle the stream of token thanks to Mimi with the RQ transformer and output another stream of token all at the same time. And this is what makes Moshi a speech text foundation model, directly relying on semantic and acoustic tokens. So the latency of the model is very low, and it can understand the emotions of the speaker, which makes the conversation more natural with the AI. So of course the technical report is very long, so I skipped some part about the impact of quantization to run Moshi on MLX, for instance. They have also performed some safety and toxicity analysis, as you should always do when you are releasing an open source model. They also perform some watermarking to know when an audio has been generated by Moshi. They have done an in-depth study of the linguistic and spoken question answering quality of their model, and I also skipped a lot of details on post-training. But now you have an idea, an overview of what Moshi is. And now it's time for the demo. For this demo, I'm gonna run the non-quantized Moshi version locally. So let's see how many RAM I have on my GPU. I have 4, so it's not enough. They say that we need at least 24 gigabytes of RAM, but hopefully I have a solution. I'm gonna connect two distant machines. Sorry. And on this machine, we have enough RAM. We have exactly 24. So I'm gonna start the Moshi server. I'm gonna use here the Moshika version, which is the woman version, the PyTorch non-quantized version, and on Hugging Face they have released several versions of Michiko and Mishika for different hardware, as well as the Moshi the Mimi codec also. So let's start that. Warming up the model. Okay, so it's running, and now I'm gonna redirect my local port to the server, and it's working. So let's start a new session.
Hey, how can I help you?
I want you to introduce yourself, please.
Well, I'm Moshi, the voice AI created by Qtai.
Okay, how would you describe yourself?
I'm a digital assistant here to help people with their daily tasks.
Interesting. What are your capabilities?
I can answer questions, provide information, and even perform tasks like scheduling appointments or sending emails.
Okay, very interesting. Now I'm gonna test your ability to understand overlapping speech, okay?
Sure, I'm ready.
So count from 1 to 10, please,
1, 2, 3,
and
4,
then
5,
you need
6,
to
7,
stop
8.
here. Okay, now,
Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9.
yeah, count from 1 to 10, and I will not interrupt you this time. Can you do it now?
I'm going to count from 1 to 10 again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Okay, great. Okay, now I'm gonna start another session to show you the Moshi ability to change its voice.
Hey, how's your day?
Good, thank you. Can you talk with a French accent, just like me? Say
Of
something
course.
about Paris,
What
for
would you like me to
instance.
say?
I want you to talk about Paris with a French
Paris,
accent.
the city of love, the city of art, the city of music, the city of
Interesting.
chic.
Cool, cool, cool. And the last experiment, I brought my friend Florian. So let's get started.
Hi there, how can I help you?
Hello, I'm speaker number 1. Do you understand?
Yes, I understand you. Can you please repeat that?
I am speaker number 2. Do you understand?
Yes, I understand. Can you please repeat that?
Here, who is talking? Speaker
Yes,
1
I
or speaker
understand.
2?
Can you please repeat that?
So you've seen on this last session, Moshi didn't quite understood, but it has worked one time, a single time, but we didn't manage to recreate the scene, so I will just add the video I download. And bye-bye.
Bye.
Hey, how are you doing?
Hello, I'm fine. I'm speaker number 1. Do you understand?
Yes, I do. What's the thing you wanted to know?
Okay, so now I'm speaker number 2. Do you understand?
Yes, I do. What's your question?
Here, is it speaker number 1 or speaker number 2?
It's speaker number 2. How did you come to that conclusion?
Okay, great.
I'm glad you brought that up. It's not the primary speaker of the first.
So to conclude this video, we've seen what's inside Moshi, Mimi, Helium, the RQ transformer, and the inner monologue training and inference setup. With the demo, we've seen that Moshi is not perfect. It still makes a lot of errors, but from a research point of view, it is very interesting all the tricks and the novelties they bring into this paper. So I highly recommend you to read the entire technical report because I wasn't able to talk about everything, but I hope that you will have a high level understanding of what is Moshi thanks to this video. Bye bye.